Well, hey, it's Dr. J. Today we're going to learn about integration by substitution. So as I mentioned previously, there is no product rule and there is no quotient rule for an integral, and there never will be. But the best we can do is we can evaluate some integrals if certain conditions are met. And I mean, it's a stretch, but you can think of this as an anti-chain rule. Yeah. And so, I mean, the idea is this, before I do any actual problems, if you have something like, I don't know, you want to take the derivative of, I don't know, 5x cubed plus 8 to the 10th power or something, right? Go to kind of recalling the idea behind the chain rule. Well, the derivative would be equal to 10, yeah, you use the power rule, 5x cubed plus 8 to the 9th, but then you'd have the chain rule multiplied by 15x squared, yeah? So, when we integrate 10 times 5x cubed plus 8 to the 9th times 15x squared with respect to x, it should go back to being this as the antiderivative. And so that would be 5x cubed plus 8 to the 10th power and then plus c, right? We're doing indefinite integrals, so we have to consider all the possible values of c. Right, so that kind of makes sense, right? If you took the derivative of a function and then you use the chain rule, you would get this, yeah? And so therefore, if you took that, you know, the result of the derivative, I'm not giving them names, I'm just saying this and that. If you took that and then you integrated it indefinitely, you would get back to the original function in which you differentiated. That's the whole idea behind derivatives and antiderivatives, right? So we have the derivative, and then we have the antiderivative. Okay, so what makes this possible? Well, first of all, you'll notice that this is sort of like a product rule. It's a very, very specific condition that must be met. And the condition is the derivative of 5x cubed plus 8 must already be included in the integrand. Right? Notice the 10 really doesn't matter. The 10 is a constant. It could have came out. So the real focus of this problem is the integrand 5x cubed plus 8 to the 9th, right? And then its derivative is 15x squared, right? The derivative of 5x cubed plus 8. So when an integral is of the form the integral of f of x times f prime of x, the integral of g of f of x times f prime of x dx. So it's a composition of two functions, f and g. Then we may substitute, and the classic letter that we use is u. And we say u is f of x. This is sometimes called U substitution, although you don't always have to use U. Sometimes people will use V or W or some other letter besides X. But U is the most common. So the derivative of U with respect to X is f prime of X. Right? The derivative of U would just be f prime of X. And then what we do is we multiply both sides by dx, thereby canceling the dx here, to get du is equal to f prime of x dx. And then we rewrite the integral as the function of u. So the f of x then becomes u by the substitution. And then the f prime of x dx becomes du. So it is just a simple way of, well, maybe not simple, but it is a straightforward way. It requires some calculation, calculus, but it's a straightforward calculus substitution of variables. So now our problem will be much simpler with respect to the new variable, which is now u. So that is kind of the idea behind U substitution, all right? And it does require some very specific contents, right? You do have to have a function that's, or integrand that's of this form. So let's do an example. Let's do the integral of 7x to the 6th times x to the 7th plus 1 to the 3rd power. Okay, so it helps if you rewrite it. It's not required, but it's helpful. Drop in here. It's helpful to rewrite it's not required, but it is very helpful if you rewrite it. And that way you have your f prime and your dx together. And so this is your f of x, x to the 7th plus 1, and then this is your f prime of x, f prime of x is this 7x to the 6th dx. You don't actually see the g of x, so maybe I'll just put a little cloud here. The g of x is the cubic. You see the power is cubed, but you don't see an actual function called g. Right? You just have to imagine that there is this, we call it the outer function. The outer function is g. The inner function is the f, and then its derivative off to the side. So by u substitution, we say let u equal x to the 7th plus 1. Then du is 7x to the 6th dx. That's going to be this part right here. So the integral of x to the 7th plus 1 cubed times 7x to the 6th dx is equal to the integral of u cubed du. So see, I hope you can see, the x to the 7th plus 1 becomes the u. And the 7x to the 6th dx becomes the du. All of this becomes the du. And I hope it's clear to the observer, to the person watching this video, that this integral is now very simple. I actually would get rid of the parentheses, and then I would use the power rule. Remember, and you could also write it as u to the 4th over 4. But remember the power rule for exponents, you just add 1 and then divide by the new power. Now you do have to switch back. You cannot leave your answer in the form of u. You do have to switch back to x. So the final answer, just use the u substitution, which is very important that you write this down so that you know who u is. So then the u goes back to being whatever it is. In this case, it's x to the 7th plus 1, and then plus c, and that is your final answer. You do not have to FOIL or distribute or combine or simplify or whatever terminology you might use for that. That's it, you know. Put it down before you break it. You could easily check your answer. I'm not going to, but I'll say DIY, do it yourself. You could check by taking the derivative. If you took the derivative of the result, you should get back the original problem, right? The original integrand. So that's u substitution. All right. A lot more examples to do, so let's go ahead and get started, or get going. All right, so how about the integral of 3x squared over x cubed plus 1 to the 5th? So it's kind of like a quotient rule, right? So what this u substitution does is, in certain circumstances, it acts as a replacement for a quotient rule or a product rule, depending on the particular problem that you have. And it only works in certain cases. It's not quite as powerful as the rules that we had in differentiation, right? Those rules were hard and fast and worked for every problem. These ones are a little bit, a little bit trickier. So again, I like to rewrite it. I'm going to write the power as a -5 power, and then I'm going to combine together the 3x squared and the dx. That's going to become u. Actually, that'll become your du. Yeah. And then the x cubed plus 1 will become u. At the very minimum in your notes, you should note, with some kind of annotation, who is u. The best way to do it is to just write off to the side here who your u is. We call this the subs, or the substitutions. So u is x cubed plus 1. And then du is 3x squared dx. This form of a derivative is what we call the integrand form of a derivative, or the integral form of a derivative. You're just writing it, instead of writing du dx equals 3x squared, you're writing it in this form by multiplying both sides by dx. And normally that calculation is done mentally. So when you take the derivative, you can say the derivative of u is equal to 3x squared times dx. Right? There's an invisible multiplication sign that we typically don't write. So then this becomes u, right? The inside becomes u. You can use parentheses if you want, but it's not required, at least not in this problem. And then this becomes your du. You do have to switch both, right? You can't have one of the variables be u and the other one be x, right? They're either both x's or they're both u's, right? Because your integral symbol doesn't mean anything without the du. So for example, writing it like that would be incorrect. Also writing it like this would be incorrect. So whatever your variable of integration is must be represented by the d, whatever, in this case du. All right. All right, and so now we do the integral. That'll be -1/4 u to the -4. Right, remember it's a negative power. So we're adding 1 to a negative power. So from -5, when you add 1, it goes up to -4. And then you're dividing by -4, which you can also write this way. These mean the same thing. It's really up to you. The key is to switch back. So always switch back. So -1/4, I usually put parentheses when I switch back. In fact, you need to put parentheses, otherwise this power won't know who it's attached to. So the parentheses are grouping symbols that tell you the final result. And there you go. Classic examples of integration by substitution. Now, these first two examples were sort of prefabricated, right? Before I, turned on the video camera, I created questions in which the subs were already there. It didn't require any creativity or manipulation in order to create the substitutes. That's not always going to be the case, right? You're going to have some problems in which you have to be a little bit more creative. We call it digging out the gold, right? It's not just going to be laying there on top of the soil, right? You're going to have to dig a little bit in there to get it. So we call this digging or panning for a substitute. Yeah. We'll start off relatively straightforward example. Now, this is an example we could have done, a week ago. And the way we would have done this example a week ago would be to actually distribute out the exponent, get rid of the parentheses, and write it out as a polynomial with 3 terms, and then go term by term by term, right? And we have done a problem very similar to this before, so you could still use that old method, all right? This does not, violate or vacate any previous techniques that we've learned. However, it makes it a lot quicker, right? This new technique. So generally speaking, we generally let u be the inside of whatever function we're talking about. In this particular one, it's a square function, squaring a binomial. That's general, right? The inside becomes your u. Then when you do your du, it's the derivative of the inside without looking at the power or the operation that's on the outside. So the du then will just be 4. And again, technically it's du dx is 4, but we move the dx to this side. So we just write it as 4 dx. All right. Now the problem is we don't have a 4 out here. Yeah, so how are we going to create a 4 right here? Well, the answer is we create a 4 right there. And the way we do it is by multiplying by a special form of 1. So whatever number you're looking for, or whatever number you wish was already there, you can wish it into a being, right? You're not really wishing, you're forcing it to exist. Right? This is mathematical alchemy, right? I mean, you are creating that gold out of thin air. Right? Now, the problem is you can't just put a 4. That wouldn't be legal. But you can put a special form of 1, which is 4 over 4. And you can do this for any constant. Right? You can do this for any constant. So you're going to get the integral of 4x plus 15 squared dx. And then you're going to leave one of the 4's outside. And the other 4, you're going to bring it in. So leave this one out. And this one you're going to bring in. All right, and so that is your 4 over 4. The one with the circle around it is the one you're bringing in. And then the other one is the one you're leaving out. All right. Remember, constants can move in or out of an integrand at free will. So now I have the integral, or 1/4 times the integral of 4x plus 15 squared times 4 dx. So that's my u squared du. Again, I'm going to write down who my subs are. U was 4x plus 15, and du is 4 dx. So that's going to be 1/4. And then the integral is going to be u cubed over 3 plus c times 1/4. So that's going to be 1/12 u cubed plus c. But we have our subs, so we got to switch back. When you switch back, you only need the u part. You don't really need the du. The du disappears through the process of integration. So put the u back in there, 4x plus 15 cubed plus c. And there's your final answer. Not too bad, huh? I drug that one out quite a bit. In future examples, I'll probably do some of the steps a little bit more streamlined, but like in the next example 4. So don't forget your plus C, capital C. Example 4. So sometimes when we have a fraction, we write the dx on the top. This means the same thing. One over 8x plus 7 cubed with a dx off to the side. So sometimes typically this only happens with fractions. We sometimes put the dx in the numerator when there's nothing else in the numerator. And by nothing, I mean 1. I know you don't usually think of 1 as being nothing, but I mean, if you wrote a fraction like that, it would just be incorrect mathematical notation. You gotta have something in the numerator. So 1 is the identity for multiplication, division, quotients, products, and things. Okay. So let's go ahead and do it. We got u will be 8x plus 7. So du will just be 8. We don't have an 8. So we'll put a 1/8 on the outside. I'm going to rewrite this as 8x plus 7 to the negative 3. And then I'm going to rewrite my dx as 8 dx. So you see, one of the 8s is a fraction, 1/8, and the other 8 is a whole number, 8. And together, that's a special form of 1. That's generally the step that we take to avoid having to write out 3 or 4 lines for that. And now we're ready to integrate. This is going to be u. This is going to be du. Yeah, by using the subs. And then we just do it. Yeah, 1/8 times. Now remember the rule for powers. You add 1 and then divide by the new power. So negative 2, when you add 1 to negative 3, you get negative 2, and then you add 1. So you're going to get negative 1/16. And then who is u? U is 8x plus 7 to the negative 2 plus c. And that is your final answer. You could leave your final answer with just a negative power. That's what I would do. Or you could rewrite it back in fraction form like this, but then change the power to positive 2 if you rewrite it. I've already boxed it. It'll be accepted, so I'll go ahead and leave it that way. All right, we're really cooking now. Let's kick up the volume a little bit and have some larger powers. Pump up the volume, some larger powers, some more complicated expressions, some things you might see on a test. One of the main reasons for these special techniques is when you have, I don't want to say ridiculous, because 19 is not ridiculous, but it kind of is. If I asked you to multiply this by itself 19 times, that would be ridiculous, right? I couldn't ask you to do that in any reasonable amount of time. Although you could do it, but I don't want to make you do that. The whole point is not having to multiply this out 19 times. Right? When something only has a product, a power that's 2 or 3, sure, you could have multiplied it out, right? In fact, I hope you could do it when the power is only 2 or 3. But once it gets beyond 2 or 3, even something like 4 or 5, it starts to take a really long time to multiply, or we call that expanding a polynomial. So that's where this technique comes into play. All right, we always typically let u be the inside function, or the one with the larger power typically. You can't let it be the 19 because that's not on the inside. It's not the 19 doesn't even have an x. It's not x to the 19th. It's x cubed minus 5 to the 19th. So we're trying to keep the 19 but get rid of the x cubed minus 5. And then we get du is 3x squared minus 0. 3x squared minus 0. Yeah, so I won't write that. Just write 3x squared dx. All right, well, we've got the x squared, but we don't have the 3. So we put 1/3 and then 3x squared. Okay. Now you can leave these separated like this, or you can bring them together. I always like to bring them together. I don't know. It's a matter of taste. I like to see my 3x squared and my dx together so that when I do my substitution, it's very clear who the subs are. And so all of this will just become du. Right? 3x squared dx will become du. And then the x cubed minus 5 will become u. You see how much cleaner that looks now? It's 1/3 times the integral of u to the 19th du. And now it's very easy to integrate. U to the 19th, you're going to add 1. It's going to be u to the 20th over 20, and then plus c. So now let's put the u back in. So you're going to get 1 over 60 times x cubed minus 5 to the 20th plus c. And there you go. Not too bad. Just to take a little breather, this would be a point where I would ask questions if we were live. Feel free to comment or to email me if you have any questions at this time or whenever you have time. But this one's a good place to just do a mental math check, right? Just sort of take a breather, think about what we've learned in the first 5 examples. So we've learned how to do this substitution. We've seen a few easy ones and not so easy. I wouldn't say this is difficult yet, but we're getting there. It's starting to pick up the pace here. But this is a good place to stop and think about how this would be correct, right? You would go back to the original problem, right? Which the original problem looked like this. So if you were going to check, what you'd want to check is you check the integrand. So you ask yourself, if I look just at the integrand is the inside of the integral symbol, ignoring the dx and the indefinite integral symbol, right? So just looking at this part here, what would you need to do to verify, if this were a test and you didn't want to take a risk, a small error causing you to lose points, how could you just easily check this? You got a couple minutes left on the clock. You can check this answer. Watch. Just go back to here and use the rules from the previous chapter. 20 times 1 is 20 divided by 60. Well, 20 divided by 60 is 1/3. Okay, got 1/3. And then you got x cubed minus 5 to the 19th power. All right, well, so far so good. All right, 19th power, good. If you took the derivative. But then don't forget, the derivative also has the chain rule. So then you have to multiply by the derivative of the inside. The derivative of the inside is x cubed minus 5, so that would be 3x squared. But remember, you have the 1/3, right? The 1/3 comes from the 20 and the 60. That's the 1/3. I'm not writing it, but it's 20 divided by 60, which is 1/3. Well, if you have 1/3 and then you have 3x squared, the 1/3 and the 3 are going to cancel, and you're just going to have x squared. So it's very easy to check. I didn't even have to write anything down. We call that checking by inspection, right? Or mental math. Just inspecting your answer and asking yourself, does that make sense? Not a bad idea every once in a while. I don't check every answer because, that would be ridiculous. We'd never be able to get through the material, but, I check every once in a while. It's an opportunity to take a breather, an opportunity to catch a mistake. Sometimes I wish I would have checked and I didn't. I go, don't. Wish I would have checked that one. All right, let's move on to another type of function that falls into this grouping. Exponential functions, natural exponential functions. All right, so The way we work these is we think of the power as being the inside. Right? So the power is x to the 7th. It's a power of a power. It's like e to the x to the 7th. Right? So that's going to be our u. It should be pretty obvious. U substitution requires that one of the two parts is the derivative of the other part. All right. And you know how derivatives bring powers down. So if you've got two different exponents, it's going to be the larger one. So because when you take the derivative, it's going to drop the power down to 6. So clearly this guy's got to be the du. Right? Well, it's actually a combination of these two to make the du. And you're going to need the 7. So 1/7 times the integral of 7x to the 6th ex to the 7th dx. And here, I'll show you one time how you don't have to bring these guys together. You can just say e to the u du. All right, so here's your e to the u. And then this and this together are your substitutes. So you got your subs. We sometimes call them U subs or U substitutions. That's it. That's it. And E is a really cool function because the integral of E is just E. Right? It's the only function that's like that. The integral of E is E, or E to the whatever power it is. So I got to be careful. The integral with respect to U of E to the U is E. It's a long way to say when you take the integral of E, you just get it back again. The same thing goes with the derivative. You took the derivative of E to the U, it would go back to being E to the U. Now, don't forget when it's that easy, you got to go back. Well, you always have to go back and put U back in. I have seen people do all the math correctly and then forget to put the proper variable back in. Right. The problem starts as a function of x with respect to x, then it has to end as a function with respect to x. We might see some functions in the future that are with respect to t. Right? We've seen those with time. Yeah. Or a function of p. We're talking about price. Or something like that. All right, some other variable besides x. Well, I'm just going to keep on rolling through these. Not a lot of variety here. It's kind of the same technique. Now the variety is going to show up in the different types of functions that we're dealing with. So I'm just going to go through the whole catalog of functions. Let's do a square root function next. Something like that. With a square root function, I think it's pretty clear who the inside is. The inside is the inside. It's 9 plus x to the 6th. We sometimes refer to that as the house, right? You're inside the house. Or under the radical. Lots of different ways to say it. So your du is going to be 6x to the 5th dx. You've got the x to the 5th, but you don't have the 6. So you put 1/6 on the outside, 1/6 on the inside. Then you substitute. The inside becomes u. The outside becomes du. Just moving right along. Sometimes it's helpful to rewrite this as 1/2 so you don't forget the rule. So it's going to be 1/6 times u to the 3 halves. Yeah, you're adding 1. and then dividing by 3/2. The 3/2 you're going to want to flip and multiply. So you're going to get 1/6 times 2/3 u to the 3/2 plus c. I'm running out of space, so that's going to be 1/9. Yeah? 1 times 2 is 2. 6 times 3 is 18. So that's 2 over 18, which is 1/9. Yeah. Or you could use some fancy canceling. You know, the 2 cancels with the 6 and makes it 3. And then 3 times 3 is 9. All right. And then go back and replace who is u is. So switch back. So you're going to get 1/9, 9 plus x to the 6th to the 3/2 plus c. That's your final answer. Don't distribute the 1/9. I've been tempted to do that myself, especially when you see these look like they might cancel. They don't, right? The 3/2 is the exponent, which prevents the 1/9 from going inside. You could rewrite the 3/2 as a square root and then a 3rd power. I don't bother doing that. It doesn't make the problem any easier. It doesn't make it look any nicer. Sometimes I do it just for show, just to demonstrate what that actually means. If I was doing an application in which I needed to come up with a final, numeric answer, then it's nice to know that 3/2 actually means the square root of whatever is inside the parentheses, and then you cube it. You take the square root and you cube it. It's nice to know that, but it's not, always required. So just kind of going through them one at a time. Normally at this time I would stop and give you a practice problem. So I would take a break and say, all right, take 5 minutes and see if you can do this one on your own. Say DIY. I don't do a lot of that in my videos because having you sit there and stare at a blank screen, or, with me not talking, is usually not very useful. So maybe instead of, just not doing this problem, why don't I just write down sort of minimal amount of work? The minimal amount of work that I would do is I would write 1/4. And then I do 4x cubed dx. I would combine these guys together. And then x to the 4th plus 2. I would also write down who my subs are. I'd say let x be x to the 4th plus, let u equal x to the 4th plus 2. And then my du is 4x cubed dx. And then there's my du, and there's my u, so this becomes du over u. Or 1 over u du. These mean the same thing. And then you have to look back at your special integral table, or special antiderivative table, or list. It requires that you memorize this. At least I ask you to memorize it. I don't have any way of enforcing that you memorize it. I hope that you're memorizing it. It'll certainly be a lot faster for you on the final exam if you don't have to flip through your notes and look that one up. Right? Just instant recall. Okay. And then you want to put u back in for your final answer. So had this been an in-class assignment, I would have stopped for a couple minutes, and then this would have been the answer put on the board. So there you go. Now, I will make one special comment, although it's not always true, so it doesn't apply to every problem of this type, but it does apply to this particular problem because the power is even and it's being added. You're adding 2 to it. So this is just a special note. Since x to the 4th is always greater than or equal to 0, that means x to the 4th plus 2 is always greater than 0. So the absolute value may be omitted. That's only if the inside of the logarithm is always greater than 0. You may omit it. So another version of the answer is omitting the absolute value, and this would also be correct. Now, that would not be true if the power was odd, and it would not be true if it was x to the 4th minus 2. So it's very, incumbent upon these two facts, that you have an even power, right, and you're adding to the even power, thereby forcing the argument of the logarithm to be greater than 0. Remember, because you can't take the natural log of 0, right, or any negative number. So it must be greater than 0. But anyway, you could have just left it. By the time you've typed it this way, you might as well have typed it this way. I have had some trouble with the ln on the computer typing. Sometimes it'll give you parentheses and the absolute value bars. Sometimes it won't let you use the absolute value bars. But I've been trying to go through each problem that has an ln in the answer and patch them up one at a time as I notice the problems. I think I got them all. But if you catch one out there that I missed, please let me know and I'll fix it. For this particular question, it should mark both of these correct. All right, the ln is actually an interesting function for a couple reasons. One thing that makes the ln interesting is that it's not intuitive why the integral of 1 over x is ln of x, right? It's something that you just have to know, right? There's not really a recipe for determining that unless you already know it. If you already know it, obviously that is the recipe, but if you didn't know it, it would be very difficult to generate that formula. That's why I recommend memorizing formulas like that, right? Some things are worth memorizing if there's no other way to know the result other than memorizing it. That's kind of true with English too, right? When you're learning to spell, long before the days of spell checkers, there were certain words in the English language that didn't really make a lot of sense the way they were spelled. And they just had some special weird spelling, right? Y'all remember, 3rd grade or whatever, or 5th grade. I don't know. You're always learning new words, right? Every year. So you can just remember any grade where you learned a word where you're like, that's a weird spelling and it doesn't seem to have any logic behind it. Well, what am I rambling about is that the ln is very much like that, where you just have to memorize certain properties about it, okay? And an interesting fun fact is that when you try to take just the integral of ln, is very difficult. Maybe I shouldn't say very, but it's not impossible, but it's very difficult. So the only way for us to be able to find the integral of the ln is to have the rule that we're learning today, the substitution rule, right? And so we will not be doing this today, all right? It's beyond the scope of this lecture. But we will be doing this one because it's sort of a hybrid. It falls into this category of use substitution, right? And we're going to first remove the 7/9. And we're just going to look at this integral. Now remember, I'm taking the antiderivative of this function, right? So it's hard to tell who's on the inside and who's on the outside. So you just have to memorize this one. When you have an ln and then another x on the outside, you are going to let u be the ln. And the reason is because the derivative is 1 over x. The derivative of ln is 1 over x. This also helps you to memorize the antiderivative, which the antiderivative of 1 over x goes back to being the ln. Although you would have to then put the absolute value bars. This one doesn't have the absolute value bars, so I guess we can assume without loss of generality that x is greater than 0. Right? It doesn't say that, but that would be a safe assumption whenever you have what's called an implied domain. Right? An implied domain is where the problem doesn't make sense unless that were the domain. So it's forced by implication. All right, so the 7/9 really means nothing. It's just there to throw you off. Although I shouldn't say it means nothing. It means 7/9, but it just means 7/9 times whatever my answer is. And then this becomes the integral of ln of x times 1 over x dx, which is u du. It's not ln of u, it is just u, because the whole ln then becomes the u. And then now you take the integral or the antiderivative. That's going to be u squared over 2 plus c. And then you have to switch back. Switch back to x. So that's going to be 7/18 ln of x squared plus c. You do need to double up on the parentheses. This is not the same as ln of x squared or ln of x squared. It's ln of x, wait for it, squared. It's not the same as ln of x squared. That's weird. Another way to write it would be, I don't know why you would, but literally write ln of x twice. I mean, the nice thing about, I wouldn't write it this way personally. I would just double up on the parentheses, but this makes it very clear that it's not the x that's being squared. It's the ln that's being squared. It's ln times ln. I've always wanted to propose this notation, but I've just never seen it. I mean, if anybody knows where that's written like that, and it's legal mathematically, I've been around a long time and I've just never seen that. We do this with other types of functions in trigonometry, sines and cosines and tangents. I can't imagine why we couldn't do it with logarithms. Maybe we do, and I've just never seen it. But I just want to make it clear that when you say this, you say ln of x squared, which is different than ln of x squared. Emphasis on your breath is important. How many more ln problems do I have? I think I just have one more ln problem. Hanging in there? Yeah? Still under an hour. Not too bad. You see how many examples I can do when I'm not doing word problems? I think we're going to have to see some word problems eventually to slow down the pace a little bit. But right now we can make a lot of progress. This is the freeway of mathematics here. We're making good time. We're going 80 miles an hour. The mathematical superhighway. All righty, well, what do we do? Yeah, what do we do? Well, you just have to memorize it again. If there is an ln and then there's another part of the function, you know, inside and outside, you're always going to sort of let the ln be the u. Right? And you can't just let u be the word ln, right? ln means natural logarithm. You have to let it be the whole function, ln of 3x. Right? Then du is 1 over 3x times 3 dx, which is 1 over x dx. And that's kind of cool when this happens with ln's, right? It's one of the reasons why I put the 3 inside the parentheses there to demonstrate this property. The only way to see this property is to have a number, a coefficient in front of the x there. And you can see that this will always happen. It doesn't matter that it's a 3. It could have been a 23 and that same thing would happen, right? So when I rewrite this, the first thing I'm going to do is bring my 2 outside. Then I'm going to write it as, watch how I write this. 1 over ln of x, 1 over x dx. I'm trying to illustrate that the du is off to the side. I don't want to see it buried inside of the integrand. I want to see it clearly pulled out to the side there. Yeah, so du is this thing right here. So that's going to be du. Okay. And then my u is down here. Oh, sorry. You almost caught me. Good thing I saw that. My u is down here. ln of 3x. And I can't change that part of the problem. All right, so this part is just x, but this part is still 3x. So that's 2 times the integral of 1 over u. So that'll be 2 ln absolute value of u plus c. And then I'm going to switch back by putting who u is. U is ln of 3x. So this one's tricky. It's got a lot of straight lines in it. It's the ln of the absolute value of the ln of 3x. Which does not mean the same thing as ln squared. Because you're not multiplying these ln's now. You're taking the ln of the ln. So it's like, it's called composition function. It's like it goes through one function and comes out, and then it goes back into another function. It just happens to be the same function twice. That's it. All right, well, in the home run stretch here, the home stretch here, example 12. X plus 4 over x squared plus 8x plus 17. So with the exponents, where you have two parts of the function that have different exponents, you're always going to want to let u be the larger one. Or maybe I shouldn't say always. You are typically going to let u be the larger power of x. So if you have a battle between an x squared and an x to the first, the u is going to be the larger one. And I hope the reasoning is clear, because when you take the derivative of the larger power, it will drop down, the power reduces, and then you'll get the other power, or the other variable. In this case, it's x. Now, unfortunately, we have a 2x plus 8 as the du, but we don't have a 2x plus 8 here. But that's easy to fix. Just multiply this by 2, and it becomes 2x plus 8. And remember, if you multiply by 2, you also have to put a 1/2 on the outside. Okay, and so then u is the denominator, and du is the numerator. So this becomes du over u, which is the same as 1 over u du, which is another ln. What do you know? So even when you see a problem and you think, oh, okay, I don't see an ln anywhere in there, but it could show up, right? Because ln has that way of just appearing whenever you have its antiderivative, or whenever the antiderivative becomes ln, right? I'm tripping up all my words. If the derivative of a function is the ln, then the antiderivative is going to appear, right? So you have the 1 over u, and the antiderivative of 1 over u becomes the ln. Oh, I don't know why I made such a big deal about that. In other words, the ln can show up when you least expect it. All right, and then now let's put the u back. Who is u is? U is x squared plus 8x plus 7. And that is your final answer. I cannot remove the absolute values on this one because the middle term, 8x, it could be negative. The result of the argument, x squared plus 8x plus 7, could possibly be negative. If the 8x wasn't there, if it was just x squared plus 7, then I could remove the absolute value bars. And if you're not, confident enough to know when you can remove them, then I always think of absolute values as like an insurance policy, right? If you're not sure, well, then you should just keep it, right? Just like you would do with insurance. If you're not sure whether or not you need it or not, well, then you might need it, right? It's better to have it than it is to cancel it and then wish you would have kept it. Right? Just like with any, insurance policy, medical insurance, dental insurance, car insurance, homeowners insurance, travel insurance. The insurance that I normally decline, though, is, if you buy like an electronic item at, Best Buy or something. I'm not a financial advisor, although I am a business calculus professor. I always say no. Because if I buy that extra insurance on like, a home stereo or a DVD player or something. Does anybody even buy that stuff anymore? A television. It usually ends up more of a pain than it's worth. And if there's something wrong with the product, I don't know. But don't take my advice. You do whatever you think is right. All right. Wow, we are almost to the end here. Let's see if I can get through all of these. I'm trying to just take you all the way to the end of substitution so we don't have to do a part 2. All right, so let's let u be the x squared plus 16x. Then du is 2x plus 16. We don't have a 2x plus 16, but we do have an x plus 8. So we can multiply that by 2. Make sure if you multiply the inside by 2, you put the 1/2 on the outside, because that's just a special form of 1. Then you do your u substitution. So the inside becomes u. Probably getting the hang of this by now. The inside becomes u. Now it is the inside of the square root. And then the outside becomes du. You could also write it this way. Same thing. I'm going to write it like this, actually. I'm not going to take either of those options. I'm going to write it as negative 1/2 power. I like to see clearly what the exponent is so that I can evaluate it carefully. All right, you remember the rule for powers? At this point, I hope so. It's probably one of the last times you're going to see it in this. Well, maybe not the last time, but the last time that I'm going to say it that way. And I'm just going to, from now on, just do it. It's going to be common sense. So we're adding 1, so that becomes positive 1/2, and then we're dividing by 1/2. So we're going to flip and multiply. Flip and multiply. So that's 1/2 times 2 over 1. And then u to the 1/2 plus c. These 2's are going to cancel. Or you can say it's 2 times 1, 2 times 1, and so that's 1. And then we're going to put the u back in. Here's my u. And so my final answer after the switchback is x squared plus 16x to the 1/2 power plus c. No coefficient out in the front because it's canceled, but we still have the constant coefficient at the end where it's plus c. You could also write it this way. This is about the only time that I do take that option. Either one of those would be fine. I usually like to see a square root if it's just a square root. When it gets more complicated and it's got other powers or it's negative or whatever, I don't really care. But when it's literally just a square root, I like to see it. That's just my own taste. Right? There's a little bit of personal preference in mathematics too. Aesthetics, what's pleasing to the eye. And if you don't have that sense, then just get it right and don't worry about how it looks. Sometimes the ugliest answers can be 100% correct. All right, well, I've got 2 special cases. So when you do this homework, it's walking the dog, right? By the time you've done the first couple problems, you're going to go to autopilot and you're going to do them all basically the same. But these last couple examples are a little bit tricky. And I originally considered doing a part 2 video, but because there's not very many of these, I don't think it deserves its own video. So I'm just going to include these, and I'll put a little star next to them, special case. All right. So what's the special case number 1? The powers are the same. Yeah. So there's no clear winner as to who is u is, right? You could be the guy on the outside, or you could be the guy on the inside, and it's not clear who wins, right? So what I did to understand this is I just did it both ways. First time I did it, I let you be the guy on the outside, and then I didn't like the way it turned out. So then I switched to letting you be the factors or the terms on the inside, and it worked out a lot better. So I'm going to spare you that because we are over an hour now, and I'm just going to tell you that the winner is the one on the inside. So when u is x minus 3, the derivative of x minus 3 is just 1. Which really just means that du is the same as dx. It also means, because they have the same power, that x is u plus 3. So we sometimes call this a double switch. It's the double switch. You have any baseball fans that are watching my videos today? That's where you switch two players at the same time. You do a double switch. Or you'll move one player to a different position, and then you'll replace that player with a new player. That's another form of the double switch. Okay. So, watch how we do this. The x becomes u plus 3. The x minus 3 becomes u. Still has the square root on it. And then the dx becomes du. The first time I saw that, I was like, oh man, if you didn't know to do that, you can be chasing your tail around and around and around, and the problem just never resolves itself. So the key here is the double switch. That is the key to this problem. You got to know to switch the u and switch the x. I'm going to go ahead and remove the constant, the 2. And then I'm going to write this as u plus 3 times u to the 1/2. And that's going to allow me to use the distributive property. So the distributive property, I can combine this all together, and so that I don't have parentheticals. I don't have the parentheses anymore. The product has been removed. All right. And now take the antiderivative. I'm saving that because I'm going to erase it right here. So I've got 2 times the antiderivative, or the indefinite integral of u to the 3/2 will be u to the 5/2 divided by 5/2. And 3u to the 1/2 will be 3u to the 3/2 divided by 3/2. And then plus c. And so what you're going to do is bring this up here and multiply. So that's going to be 2/5. That's going to be 2/3. And then you're going to distribute this 2 here. So you're going to get 4/5. And you're going to get 4, because these 3's are going to cancel. And finally, put u back in. So you're going to get 4/5 x minus 3 to the 5/2 plus 4 x minus 3 to the 3/2, and then plus c. Oh, my battery's about to die. That tells me we're almost done. My battery life usually gets through one lecture before it's about to die. There you go, folks. That's the special case number 1, the double switch. Special case number 2 is another example of the double switch. Although it is a little bit trickier. I'm just calling it the double switch with bacon, I guess. I think I'm ready for lunch, because that just sounded really good. I'll have the double switch with bacon. Hold the fries. All right. Yeah, I usually don't eat the fries. Unless they're really good, really fresh. I'd rather just not have French fries than have the extra junk food. I mean, not that I'm a health nut or anything. You only see me from the chest up, but I should probably learn to eat better, especially now that I'm in my mid-50s. Almost mid-50s. I'm getting there. I'm getting old. All right. You can tell by the shirts I wear, right? I'm ready for retirement already. Okay. This is the last example. Special case number 2. With bacon. All right. The same kind of idea as the last special case. Now, this one's tricky because in the last one, there was no clear winner, right? But in this one, if you use the rules that I taught before about the larger power would be the U, you would run around in circles and never get the answer. I've tried it that way. Yeah. In fact, when I first learned this, nobody told me the trick. Like, we learned by suffering, by doing the problem incorrectly a bunch of times until somebody, says, hey, there's an easier, softer way. And then you go, fuck, I wish I would have known that. It could have saved myself a lot of suffering. But that was the old way to learn, right? Learn through trial and error and extreme pain, okay? I'm trying to save you the pain. Now, if you want to feel the pain, just to feel what it's like, Throwback Thursday or something, what was it like back in the day? You could put on an old vinyl record and do a math problem like we did in the 80s, right? I'm going to spare you that. So instead of choosing x to the 7th, the larger one, we're going to go ahead and choose the one in the middle, the x to the 4th. So we're going to let u be 7x to the 4th plus 10. Then du is 28x cubed dx. Right? And then this one's kind of tricky. Watch. We don't have a 28, so that's easy to take care of. We can put a 1 over 28 on the outside, right? And then put a 28 on the inside. That's easy. We don't have an x cubed, but we do have an x to the 7th, which we could break up. This is the bacon, double switch with bacon, right? And you got to see that. You have the x cubed, and then you have an x to the 4th, right? Now watch this. Here's the double switch. X to the 4th is u minus 10 over 7. That's the double switch. Right? So double switch means you switch one of the variables to become u, and then you switch the other variable, the x, to also be u. You're doing a double switch, but they're two different versions of u. Yeah, you have this u, and then you have this u. That's what we call the double switch. So watch this. All right. So this x to the fourth becomes u minus 10 over 7. This 7x to the fourth plus 10 becomes u. And then these guys, 28x to the third and the dx, those guys marry together to live happily ever after, well, at least till the rest of this problem is over, and then they break up. Okay? So they'll last till the end of this problem. All right, now check. It keeps going, all right? It gets even better. The 7 comes out, and you go 7 times 28. What's 7 times 28? 168. Still doing the old school calculator. My phone is in the other room. 198. I'm glad I checked. 196. Oh, man. Definitely glad I checked. My brain's getting tired. So the 7 comes out with the 28 and multiplies, and you get 1 over 196. Then this becomes u to the fourth minus 10u to the third du, because you have a u to the third multiplied by 10. That's pretty straightforward. And then you have a u to the third multiplied by u, which is u to the fourth. Whew. We're really cooking now. I mean, this is calculus. Welcome. You know, sometimes when you do calculus, you go, man, that was it? That was calculus? Oh, I can do that. But then sometimes you do calculus and you go, man, this is calculus. This is the reason why it's an advanced level college course, right? This is not for the faint of heart or for the unprepared student. Okay, so we're going to need this. Let's save that. All right, you actually don't need the other switch. So that's you do the double switch, then you take the integral, and then you go back to only the first u substitute, and that's the one you actually need to save. All right. So I've got 1 over 196. Now the antiderivative of u to the fourth is u to the fifth over 5. The antiderivative of 10u to the third is 10u to the fourth over 4, and then plus c. I'm going to go ahead and distribute the 196. So times 5 will be 1 over 980 u to the fifth. And then we'll have 5 over, so 10 divided by 2 is 5. 4 divided by 2 is 2. And then 2 times 196 is 392 u to the fourth plus c. And your final answer, you made it. 7x to the fourth goes back in. You got to switch back. And the same thing here. 7x to the fourth plus 10 to the fourth plus c. All right. Thanks for hanging in there with me. That is the end of integration by substitution. Although it's just the beginning of the chapter. And now that we have the first couple sections under our belt, we can really move forward, make some progress, and get back to business. We got a few more things to learn until we're ready to really tackle anything substantial. But, you know, really focus on these last couple lectures, last couple sections. It's the bread and butter of chapter 4. It's going to help you be successful, leading you all the way to the final exam. But until my next video, keep working hard, keep doing your homework. I'm Dr. Jordan, and I'll see you on the internet.